Hi everybody, this is the second part of the ESP Basic series related with the PCF8591 IC. If you remember, last time we were talking about driver implementation for the DAC part of the IC. Today we will continue and we will start talking about the ADC part. If you remember, also from last time, we have identified the four ADC inputs here on the right side, yeah, and we will jump soon on the datasheet and we will see exactly how they can be chosen and how they can be driven, yeah. For this example, I will use only the input 0, so the first input of the ADC, and to be able to use it, I will just remove the corresponding jumper, yeah. So basically I just need to remove this jumper from here, yeah. It's the jumper that is connecting one of these resistors to the ADC input, yeah. So now with the jumper removed, this input hopefully will be free, open free, yeah. I'm thinking to go a little bit further, and I will try to use in the same time also the DAC output, yeah. So basically what we will try to do will be to set a voltage here on the DAC output, and after that we will try to read the voltage on the ADC input, and we will take a look on the results to see exactly how accurate it's this IC and how accurate and what's the difference between the output voltage of the DAC and the input voltage that we will receive on the ADC, on the input 0 of the ADC, yeah. So to achieve this one, I will just connect a jumper between the ADC output and the DAC output and the ADC input, yeah. So this is direct connection. Also remember from the last time the problem that we had related with the DAC output, especially on the higher interval, yeah. After 2.8 volt we start having problems, yeah. And we just find out that it was related with the fact that this LED is connected directly to the DAC output, yeah. So don't forget to remove this resistor from here if you want to use it for anything else than playing with this LED, yeah. So this one need to be removed, yeah. Okay, so this is the PCF8591 board setup for today, yeah. Removing the jumper from here, there, and also to remove the resistor from here, yeah. The connections are the same. On the next bus we will just connect the board directly to our next evolution board, yeah. Okay, so that's it. Let's jump on the software side, yeah. So what I'm thinking to do today, I think it will be better if we are just starting the program, and we will see how it's working, and after that we can start talking and explaining on the code what's about, yeah. So the setup, as I said, it's it's very simple, the same thing as last time. Yeah, so we have the PCF8591 board connected directly to the next bus. Yeah, so it's the standard connector. You will find out that there are around a lot of demo boards and small teeny boards that are compatible with our next bus. Yeah, okay, so it's connected, everything is okay. You can see the power LED, it's on. Don't forget about the jumper. Yeah, so remove the jumper from here and move it up to connect your DAC output to your first ADC input. Yeah, so this is from the hardware point of view. Now let's quick jump to the software side. Yeah, regarding the software, as I said, first we will run the program, and after that, with the program run in mind, we can start and talk about the implementation. Yeah, so this is the new software. Actually, what I have done, I have just taken the DAC driver that we have write it last time, and I modify it to use it for the ADC demo. Yeah, so this is the program. Let's run it. This is how it's looking, the interface. I will explain you a bit what we have here. In the upper side we have the DAC, yeah, because we said that we will use the DAC output as an input for the ADC channel 0. Yeah, so basically if we are setting the DAC to, let's say, about 1 volt, yeah, this is the DAC output voltage. Yeah, it's about 1 volt. Soon as we start the ADC 0 channel, we will see a similar value. Yeah, so as you can see, DAC input value is 79. That means translated in about 1.112 volts, and ADC 0 read value is 78, and that means about 0.9984. so we have here one bit error. Yeah, okay, let's try another value. 100, 1.28, 1.26 back again, 99 and 100, and so it's still keeping 1 bit behind. Yeah, 150, 150, 192, 19, 149, 150, 1 bit. It's quite constant, one LSB behind. Yeah, 200, 199, 2.56, 2.54, and the maximum value 255, 3.264, and reading 3.2512. Yeah, so it's one less significant bit difference between the output of the DAC and the input of the ADC. Yeah, on the lower interval it's 0, 1, so you can see 20, it's 19. If it's keeping constant 1, then it's very easy to solve the problem, because we will just add 1 and that's it. It will be the same thing. Yeah, so let me try 40, 50. Yeah, it's about 1. So if you just add 1 here, the values will be spot on. Yeah, okay, so this is how it's working, this very simple driver. Yeah, let me stop the program, and now let's go on the software and see exactly what are we doing here. Yeah, Okay, so if you remember from last time, the first thing that we need to do is to properly choose the I2C address for the PCF8591 and also properly set up the I2C bus, choose the proper SDL and SCL pins, and so on. Another things that we have done last time were related with the DAC. So we just initialized the DAC variables. Now we have also some variables for the ADC, and of course we have the very important voltage calibration value. Yeah. In terms of the DAC input, it's the same thing as last time. So basically I have a text box where you can input the DAC value and the button that you will press, and when you press the set value button for DAC, it will jump in the set DAC subroutine, yeah, where the DAC value will be updated as a DAC multiplied with the voltage calibration, yeah. And after that we have the communication with the IC. We will start the I2C bus. We will write in the config register the corresponding values for enabling the DAC, yeah, and it's 64. And if you remember from last time, it's 64 because it's the 7th bit in the control byte, yeah. Just let me go again. Control byte, yeah. Just let me go again on the control byte, yeah. So we are back to our control byte, yeah. So it was the 1 2 3 4 5 6 7th bit, the DAC output enabled, yeah. So that means 64, yeah. And after that we just write the DAC value and that's it, yeah. And we find out that it's working very well. Now what we have done in terms of the ADC, as I said, this time we choose to use only one channel as an example, but the same thing is happening also for the other channels. It's no difference at all. If you want to use all the 4 channels, then of course you can enable them, yeah. For the ADC, we will read some values that will be printed in the text box, and we have also the voltage that will be printed in the text box, yeah. And a start ADC and a stop ADC button. When you are pressing the start ADC button, it will go quickly in the ADC 0 routine, yeah. So this subroutine ADC 0, what it's doing, it's starting a timer that it's calling every 1 second the read ADC subroutine, yeah. And in the read ADC subroutine, what are we doing? We are defining the channel that we want to choose, yeah. And after that we will start the communication with the IC. The first thing that we will do obviously will be to start the I2C transaction, yeah, the I2C communication. After that we need to write again the corresponding value in the configuration register, yeah. So this one is jumping us back again to the control byte, yeah. And in our case it's the same value, 64. So why it's 64? It's very simple. For our example, what we need to start the ADC 0, but in the same time we need to keep the DAC on, yeah, because as you remember, we are using the DAC as an output for our ADC, yeah. So it's not enough to start the ADC, you need to be sure that you are keeping also your DAC on. Yeah, so 64 in the control byte table, we will see that 64 means DAC output. Yeah, we know from last time this is DAC output. Why is not change the value? It's very simple. On the AD channel number, we just choose to use channel 0, and channel 0 means 00 here. Yeah, and because it's 00 with 64 means purely 64. If you want to choose, for example, channel 1 in the same configuration, and if you want, you can run this exercise. Yeah, for 01, then you have 01 plus 64, because you need to keep the DAC open. Yeah, and means 65. If you want channel 2, means 66. If you want channel 3, means probably 67. Yeah, this is how it's working in terms of AD channel number. Yeah, we will not use the auto increment flag. We will keep the input as single-ended. Yeah, so here it's 00. But again, for example, if you want to use it as a differential, you can do it as two differential inputs, for example. Yeah, this will be channel 0 differential, and then you will end up with 64 plus 32 plus 16, yeah, and so on. You will add them all, and the value, it's the value that you need to write here for the configuration register. Yeah, so this is how you build up your control byte. And as I said last time, with this table and with this control byte, basically you are driving the IC. Yeah, okay. So now back to our story. We are writing in the control register 64, so we will start ADC 0 and also keeping DAC on. Yeah, we will end this transaction where we are telling the IC how to be configured, and after that we are, so this was, if you want, the write transaction, and now we will start and use the read transaction. Yeah, so to read back, we will just use I2C request from instruction. Yeah, that means it's telling to the IC at the address that in our case it's 72 and it's actually PCF8591. Yeah, that we want to read 2 bytes from it. Why we are reading 2 bytes? We are reading 2 bytes because this is how it's sending back the values. Yeah, if we are looking on the AD, yeah, we will see that it's sending you all the time the 2 values. Yeah, so basically you have one value and another value and another value and another value. Yeah, okay. So we can just ask for 2 bytes. Yeah, we have a just small settle time, and after that in the variables ADC00 and ADC01 we are just doing I2C read. Yeah, and we will read the first and the second byte. Yeah, and of course we will end the read here. It's a read transaction. Yeah, after we read the bytes, we have the values. Now with the values obtained, we can see what was the value of the voltage that we have read from the ADC, and for that we are just calculating the ADC 0 voltage as the ADC01 value that we obtained from the ADC multiplied with the same voltage calibration. And it's normal to be the same voltage calibration because this voltage calibration it's only dependent on the supply voltage in our case, yeah, and because it's only one supply voltage for one power supply voltage for the ADC and DAC and basically for the whole IC, it's the same, yeah. Okay, so this is how it's working the read ADC subroutine. We have another small subroutine that is called exit ADC that is helping us to stop the ADC reading, yeah. So we will stop the data acquisition from the ADC. In this case we just stop the timer that you remember was calling the read ADC subroutine every 1 second, yeah. And of course we have also nice elegant exit button to properly end up the program when we will finish, yeah. So that's it. Let me save it and let's give it a very short run. Input DAC value will go to 79. I know that it's around 1 volt. As you can see, ADC is stop. I will start the ADC and the read voltage is 0.9984. It's very interesting to see that it's stable on the whole interval, only at one less significant bit difference. It's interesting because that means that it has a very good linearity, you know. When you have these cheap 8-bit devices, sometime to the end of the interval you can see things moving out from the linear stage, but this one is looking very good. So yeah, just adding another LSB to the ADC I think will make it spot on, yeah. So if we take the voltage calibration and we will say voltage calibration plus ADC01 multiplied with voltage calibration uh, 79. Let's start the ADC. As you can see now, the values, yeah, are 79 and 78, but the voltages, yeah, the DAC output voltage and the ADC read voltage are the same, yeah, because we compensate that missing LSB in the calculation of the ADC read voltage, yeah. And now if you are going to 250, you see the same thing. We have 250 3.2 volt, 249 3.2 volt, yeah. And to the lower side 0.26 20 for the DAC, and ADC read value is 19, but it's compensated, yeah. It's looking very nice actually. I must say that it's very stable. It's very stable. Jumping a bit, but 1 bit, 1 LSB, it's quite impressive, yeah. Okay, so this is actually all about the PCF8591 DAC and ADC driver. As you have seen, it's quite easy to be used. So you can just take your boards and run your tests, and I will be happy also to see your results. So that's all for today. Again, I thank you very much for watching, and if you like my work, then please give me a big thumbs up and please subscribe. See you next time.